All right. Welcome back, everyone. Can you hear me okay? Someone send me a note in the chat here if you can hear me. Yep. All right. Excellent. Chat is disabled. Oh, okay. Not sure why that would be. Let me check. Okay. Well, at least you can use the question and answer. So, all right. So thanks for returning for week 2, everyone. We are going to just go ahead and get started so that we get through everything. We have kind of a lot to do today. So let me share my screen. We'll start going through it. And actually, we're going to start with a little review from yesterday for things that I didn't cover and things that came up in terms of questions from last week. Okay, so yeah, as a reminder, yeah, questions questions are good, either in the chat, and I'll get to them if I can, or the Q&A, or on the issues page. And if all else fails, you can email me. But to recap, last week we set things up to, for you guys to have a system that is going to be, productive for you with the Blazor templates. Hopefully you guys have been able to get that to work on your computer systems. Using Git and GitHub previously in this course was sort of extra credit, but now more and more I'm just recommending it, and we're just going to go through it and use it because it's going to keep you organized and be able to, turn back time on things. And I'll show you how you can do that today. Scripted commands are going to make Git easy for you to use so that you don't have to go searching and trying to figure out every time what to do. And I realized last week at the end we sort of didn't go through how to finally use Git after you got it set up. Setting up is the hardest part. So once you've got it going, it's really super easy. So let me just demonstrate that for you. Okay, so I'm going to go over to my RStudio here. Okay, and so these are the basic Git commands that we're going to use in the class. Again, I mentioned last week, if you're collaborating with someone like your PI or another student or whatever, you're going to have a slightly different workflow built in that, if you're going to use this template. It's really not that much harder at all. But I'm just going to keep it super simple. We're going to use these commands here. These are on gitcommands.r under basic everyday commands for all Git users. Okay, so what you'll notice is that I've already made some changes to one of the files in here. It's a very minor change. We can click on that thing, see what it is. I just added this little comment. So we're gonna go through that comment later today, but so there's just a tiny change here. And let's say I want to, make that a new commit or a new save point on our project. So we can just run through these commands here. So the first thing, we run through this, it says git status. That tells us, basically summarizes all the changes we've made to the files in our project. You run this. This is a nice thing to do. I know some people over the course of the week were having difficulty with this particular command. If it errors for you, it's not the end of the world. What this command does is it goes through all of the R scripts in your project, and it finds all the packages that you're using, and it writes that into a file. It updates a file that's carried along with the package. The reason that's nice is because, and the reason why we do it when we're doing this Git stuff is in order to have a reference for this exact state of our project. So whatever things that you did, whatever you produced with this project at this point in time is going to be dependent upon the code and also all of the packages and software that you're using. And that's what's notated in this library catalog. That catalog lives here. It's this Blaze02 project.tsv. And that's all just carried along with your project. All right, so that's what that does. This command here, git add, that what that does is it then indexes everything. Git goes through, figures out exactly what all the changes are, and saves those changes in the sort of its internal state. And then commit is, so we've done that. And then the next step is to do the commit. All right, so we'll just call this, and this is where you get to add your sort of comments about what this was. So we'll say this is some minor changes before class. Okay, so we can run that, and you'll notice what happened here is that this Git panel changed. So there's now no changes because we made a new commit. Everything is clean now. All right, so we're at a new save point and there's no changes in our project. All right, and then the last thing we can do is we can run this command to push the changes to our website, which is GitHub. All right, and so we can go to the GitHub website, which is going to be right here. And if we then reload this, you'll see that there's some minor changes before class. That's the last thing that we did. Yeah, so now everything's up to date here. If we wanted to say, oh, I deleted a file or I made a change that I don't like, I want to go back in history, easiest way to do that is go to this website, your website, not mine. Go to your website where you're doing all this work, click on that thing there, and you can find all of your historical commits, all of the saved states of your project, going back to the very beginning. All right, you can say, oh, I want to go back to that one there. You click on that one, and then you click on browse files over there, and that gives you all the files at that particular point in time. And then you can just open that file and open that, and then copy and paste or save it, however you want to do it. All right, so that's actually the easiest way and most common way that I will go back in time to find something. All right, so a question in the chat: how is GitHub different from something like Jupyter Notebook? So I don't use Jupyter Notebook, so I'm not sure precisely what questions you're trying to get at here. But notebooks in general are sort of interactive coding environments, and which in essence are text files. Okay, these are text files that connect to data, that run programs, whether it be in Python, which is a Jupyter thing. Actually, Jupyter used to be Julia, Python, and R. It's now mostly Python. Or an R notebook is another version of that. So they're just text files. GitHub is just a website for tracking changes to text files. All right, so they're not really the same concept, but you can use GitHub to track things that you've done in a Jupyter Notebook. Okay, so hopefully that makes sense. All right, so that's the Git thing that we wanted to finish up from last week. Now, I know a number of people had some issues in terms of basically establishing, these files and these directories that we're using for the Blazor templates program on their computer system. And I think, this is something that really, I should have gone over, but is really sort of a basic, sort of feature of working with your computer. And, sort of like you sort of have to work with your computer and not against your computer. So it's not, it's just the way computers work, and you just sort of have to learn it. And one thing that has came up a couple of times is, sometimes in like example code, like on websites, we'll put in like placeholder text. So if I was going to tell you to create a directory, maybe I would put that inside those little angle brackets. Well, you don't ever want to include the angle brackets. You want to replace those with like your own text. And the angle brackets just mean that you replace that whole thing with something that's specific to your computer. All right. And usually, you might not get an error, but computers don't like to have that particular symbol in, say, file names or directory names. And you might get errors doing that. And anyways, you just don't want to have those angle brackets in there. So if you ever see those angle brackets or, sort of something that looks a little bit strange, don't include it. Just like fill that in with your own stuff, like your own like home directory, for example. So next thing is this tilde sign here. So basically this is a relatively universal like symbol for the home directory. And generally it applies to Linux and Mac and Windows. So basically any platform you're going to be using, this is what it means, your home directory. Now, precisely what the home directory is depends on your computer. And it may be a little bit different, depending upon how your computer is set up, particularly if it's a Windows computer or if you're using like a cluster like the Ohio supercomputer or something like that. The definition of your home directory is going to be different. Regardless, the tilde is always going to take you or stand for that home directory. Okay. Now your home directory is not sort of like the most basic or root directory. All right, we'll get to that in a second, but it's sort of living within like maybe a few directories down, so nested within some other directories. So whatever that nesting, path is, that's what that tilde stands for. All right. You may or may not want to be working in that particular directory. So depending upon your computer, it might be better, make more sense to work in a dedicated directory for your projects. Okay. And this can be, and then you can have a subdirectory for your R projects and then maybe other directories for other things. But sometimes the home directory has some special files in it that you don't want to accidentally override or delete, or maybe the home directory doesn't have enough space to be useful. So in any event, that depends on your system, and you'll have to figure that out. What's the best directory, or maybe someone in your research group can help you with that. The next thing I want to point out is that whenever you see this slash at the beginning, okay, so slash at the beginning, all right. That means it's what we call an absolute file directory, okay? And absolute means you're starting from the root directory, which is sort of the most special fundamental directory that contains all the files that makes your computer run, all right? So you don't ever want to be in that directory itself, like the slash root directory, all right? That's like, first of all, you're not going to usually have permissions to do anything there. The other thing is that, even if you did, like if you overwrite something in that directory, it's going to like break your computer. So you just don't want to do that. However, it may, under certain circumstances, it may be helpful. You may have to use that as a component to find out exactly where you're at. And so let me demonstrate that if I can here. All right, so I'm actually going to go. We can try this one here. So if I run get wd, I run that there. So you can see, this gives me a absolute file path starting with the slash. Okay, so that slash is more or less considered the root directory on this computer system, which is the Ohio supercomputer. Okay, so I can't write anything in that directory, the slash directory. I can't change it. I can't do anything in there. And actually my home directory is this much there. Okay, so so hopefully that illustrates that for you. If you have to say, all right, I want the whole absolute file path, you're going to do that. Now let's say you only want to make a relative directory. Well, you can create a new file relative to the directory that you're currently in. And I'm in this project, okay, the R class project, as we all know. And if I were to say, make a command here that says, file.create, that will create a file. And we can name that file test.txt, okay? And if I run that, it's create a file relative to my current directory. So I didn't put any slash there. I didn't put any tilde there. It's just the name of a file that puts me in this directory that I'm actively in right now. Okay. And just to illustrate the fact that I can't write, I can't write to the root directory, I'll say, slash, and we'll just try, oops, text. Okay. All right. So I can't do that. So warning, cannot create file, permission denied. All right. So that's the difference between the root directory, which I can't write to and I shouldn't be writing to, versus a relative file path. Okay. So that's the root. That's a relative file path. Okay. Good. Hopefully that's clear. If you have any questions or confusions with that, let me know. Okay, so now we're gonna move on to like actual R data stuff. So that's hopefully going to be a relief for everyone. Okay, so let's just get started here. This is the script that we're going to use today. It's already been pushed up to my GitHub if you want to look at it. More or less the important stuff is also here in the notes that we're going to go through. And the first thing I want to say about data is that there is a sort of well-established theory about how to maintain data, okay? In particular relating to databases and how different pieces of data relate to each other. What's the best way to maintain those data so that there's a minimal risk of confusion, of duplication, with sort of the best and most efficient storage, okay? And, these do not include things that, maybe I used a long time ago, and maybe many of you use now, like Excel, with complicated spreadsheets and different values and merged cells and, these sorts of things. None of those are standardized in a way that's easy for a computer to interpret. And they are liable to being misinterpreted by a computer or another user more, more problematically. So if, there's one thing that's important about this whole lecture and even about this whole course, it's when you're saving your data, save it in a way that makes sense from a computational perspective. And then that's going to be a standardized format that, your peers, your collaborators, your PI is going to be able to understand and interpret and help you with, okay? So, and basically this boils down to having things in flat text-based files, okay? Most commonly a CSV or comma separated values file, all right? And, the difference between, Excel can handle a CSV file and it may look similar when you're working with Excel to a .xlsx file, but they're very different on the back end. An XLSX file is a binary compressed file with a lot of other mumbo jumbo in it. And then that's going to be a lot more challenging for you to keep track of and work with. So what about this? So I'm going to demonstrate this in a moment, but the principles that you want to maintain are that each row, all right, in your CSV file is going to be an observation, okay? And that can be, let's say you're doing an experiment on mice, that can be, each row can be a mouse, each row can be a patient, each row can be a sample. Maybe if you're doing single cell RNA-seq, each row is a cell. In any event, each row is an observation, and each column is an attribute or a variable that describes that observation. So if you're measuring certain things about a mouse, if you're measuring certain things about a cell, or if you're, basically describing or classifying a cell in certain ways, each of these can be an independent column in your table, okay? Each column is a single specific data type. So, this, is often a thing that comes up when you're working with Excel, is that, you'll type in the number, some number, for example, and then you know, maybe you'll put like a % sign in there, and then it will change the whole column to being, you know, not numbers, but then now text, and so it's not really very clear. So what you want to do is you want to make sure that, you know, if you're putting in whatever goes in that same column, all the observations are maintained with the same data type. Okay, and we're going to go through, you know, how to be explicit about that in R and how to check that when you're loading your data in. The next thing and the last thing on this point is, you know, each row needs to have a key. All right, and you know, this can be sort of theoretical in some ways, because maybe a key is you know, just the row number, and maybe that row number is doesn't need to be explicit. But you know, when you're working with, say, multiple different types of observations on your experiment, it might be most efficient to keep different types of data in different tables, and you want to have a value that links similar or basically the same biological sample or same biological you know, set of observations between those different tables. So having a key is really good practice, and like the easiest one that we're going to get to when we do single cell RNA-seq is like the barcode. Okay, so barcode is a great concept. It's unique. There's only one barcode possible for, you know, a whole set of data. Sorry, for each cell in a whole set of data. You can't have duplicate barcodes, otherwise there's a collision and that's an error, right? So you want to make sure that there's a unique identifier for each piece of data. All right. So the other point that we want to make is how to sort of like treat these files. All right. And the way that I feel is the best, and I think most people would say is the best, is to, you know, have the data live in a relatively pristine state on your computer. Okay, and that can be on a network drive. Obviously, ideally, it would be backed up, you know, so that, you know, it's not on a laptop that, you know, gets lost or something like that, or a thumb drive or something like that. But it should be fixed and unchanging, so that, you know, you're not always going back into that to, say, calculate a new value based on that original data file. You want to leave that data where it is and then read it into your R session, and then do all of your manipulations in the setting of R. And R is perfectly capable of doing all that. So you want to use that, and that becomes the processing that you're doing on your data, calculating averages, you know, doing whatever that you're going to do. All right. So don't be messing around with the CSV files. Let those live in a sort of a pristine state. What you can do, you know, when things get when you get more and more things, and that becomes labor intensive to repeat that every time, is you can save these things, save like the process data as a data package. And we're going to get to that at the end of the course. But that's particularly useful when you're doing single cell stuff, which is complicated. The calculations are intensive and they take a long time. So, okay, so let's start to just demonstrate some of this stuff. All right. This is, you know, when you set up these projects using this template here, it's going to give you this dependencies.r file and this configs.r file. So this is the way I prefer to work. You don't have to operate this way, but we have these library commands here. What these are is it's telling your R session to attach a certain set of functions to make them available to you. All right. And there's certain ones that we just use all the time. And so I think it's most convenient to call these all together on a dedicated file. All right. So when you sit down to work, usually what I'll do is I'll sit down and I'll click source to source this dependencies.r file. Okay. And everything here ran. We've now attached all these very basic functions to our session. Okay. Next, we have this configs file. Configs are usually, in my view, a question here, do you have to reattach libraries each time you run a new session? The answer is yes. So every time you sort of restart the session, let's say I want to do, say I do that, I want to restart the session, it's not going to know. Basically, the slate is wiped clean. There are certain default packages that that get attached automatically, but they're not going to be. You're going to want to have more than that, right? So now I have to run that again. It's not going to know. Anyway, you can bypass attaching libraries each time. You can, and I'll show you how to do that. All right, so we're going to source that. We're going to run that again, but really, it's not. Usually you want to do that. The configs file I have for more sort of transient or less, more like, I guess, sort of lightweight type of things. These are the most important things you'll find on here. So this conflict. So what can happen is, let's say I have attached, this particular package called dplyr. All right, that's a very useful package we're going to go through. Contains a command called filter. Well, if I typed in filter, what's going to happen? We'll say filter. All right, well, the problem is, it says here .conflicts. Well, it's detected a potential conflict with that name filter. All right, so filter is available in dplyr, but it's also available in the base package. So how is R supposed to know if I want to do the dplyr filter or the base filter? Well, you have to tell it. Otherwise, it will pick one at random, which is usually not a good way to go. So what these statements do here is it tells R, conflict preferred, tells R to select the dplyr version whenever I say filter. All right, and that's a very useful thing. So we're going to source that. It says here, so conflicted will prefer filter from dplyr over any other package. So that's useful. All right. So let's say you didn't do that. You didn't want to do that. You can do this notation here. So what the two dots mean is that explicitly states what package that command is going to come from. So read underscore CSV, that only really lives in the reader package. All right. But if I hadn't attached reader with these other commands, it would not know where to find that. So I'd have to explicitly state it. So if you didn't want to run these library commands, so reader lives inside this tidyverse package, then you would have to do that for everything. So it's, more or less up to you how you want to do it if you want to type all these different package names out every time. Okay. Another thing that you can do is you can simply, let those live here on this file and then run these types of lines here. So source, that will just in the background source that whole file. It does the same thing for you. Same thing here. Okay, so that's another way you can do it, just to make it more automated and self-contained on the single file. Okay. All right, so first thing we're going to do is we're going to read in some data. So this is basically a very standard example data set that we have in R. It's on my website because I made a couple of changes to it that we'll see here. Okay, so I run that command and it happens very quickly. All right, so what do we get? So it's giving us some messages here. It's imported a certain number of rows and columns. Okay, this turns out to be very important. All right, it's imported one column, which is a character, and 5 columns, which are doubles. All right, what is double? Double basically is a numeric value. It's a synonym for numeric. And we can look at it down here. Give us a little preview down here. It's a tibble. All right, a tibble is essentially the same as a data frame, which you might have heard of. This is the most useful format for your data to be in. Okay, so a CSV file, any sort of tabular data is most efficiently used as a tibble or a data frame, but I prefer tibbles. Okay, tibbles just because the functions that operate on tibbles are more convenient. Okay, so as I said, there's 1 character and 5 numeric columns that were imported. Okay, and you can see here with these that these symbols indicate what those columns are. All right, each column has a header, as you can see there. So what are these things? Well, there's a number of observations, 140, 150 observations, okay? This is our key, observation number 1 through 150, all right? And then there's some data here, all right? Measured that sepal length, sepal width, and that measured the petal, et cetera, et cetera. And here's a character, all right? Character is what it sounds like. It's letters in this case, all right? All right, so that's useful. But so like what kind of data types are there, right? Well, there's a few, all right? So there's character, which is, like I said, letters and numbers treated as characters. So 1 can be a character as well, or 2 or 3. Numeric or doubles. Integers are sort of a special case of numbers, or somewhere in between numbers and factors. So numeric is essentially real numbers. Integers are integers, so 1, 2, 3, 4, 5. We use those sometimes, not often. Commonly we use factors though, so factors can be a little bit tricky, but it's important to know what they are. A factor is essentially a character value that has an order to it. Okay, it's and really what it is, it's a character label, like say in Word, like my name, Brad, is a word, attached to a value, say 1 or 2 or 3. And so there can be an alphabetical or an intrinsic ordering to character values, or you can set it explicitly by rearranging those number orders. Okay, so there's a lot of techniques and tricks to doing that. What it boils down to is you're going to use that most often for ordering things in a plot, ordering things in a figure that you're making. All right, you want column 1, 2, and 3 to be in a certain order, then you'll use factors to establish that order. All right, so we'll show examples of that. Not this week, but next week. Okay, so let's look at this a bit more. So observation as a double. Well, it's not really useful as a double. It's not really a real number that we're caring about there. It's simply an ordinal number. It's like the first observation, the second observation. So that's not really something we want to have as a double value necessarily, or a numeric value. So we can actually explicitly tell R to change that when we import the data. All right, and that's what this additional, everything up here is the same except for this bit here. Okay, and what this little string of letters here is, it tells us to make the first column a factor, these next 4 to be numeric doubles, and the last one to be a character. Okay, all right, so I run that, we get slightly different. So now observation has become a factor. Okay, so we're now treating observation as an ordinal or a categorical variable rather than a numeric continuous variable. All right, that may look pretty subtle and maybe you don't understand or it doesn't make sense as to why that matters, but when you go to like visualize these things in plots, it's going to be treated differently depending upon the type of variable that it is. So whenever you're importing data, you always want to make sure that it's imported properly. Okay, R is going to make some guesses as to what it thinks it is, but you got to make sure that that's correct. Okay, all right, so all we've done now is basically read that file off the web and then spit it out into the console down here. So that's like not the most useful thing to do. So what you want to do is then save that value, save that data as a variable. All right, and so this variable is going to be something that you can then work with later on in your script or in your session. Okay, so I'm going to do that here. The way you do that is with this left pointing arrow. All right, so we've now, you'll notice that it copied the command down here, but it didn't spit the value back out in the console. That's because the value got saved into the environment. All right, and there it is. That's new. That just showed up. Demo data. All right, so I've now saved that or stored that in my global environment. Okay, definitely put some comments here in the chat if you have any questions about this stuff. All right. So now then we can run that command, just basically running the name of that variable. It will then spit it back out into the console for us. Okay, so that's now saved and it's something that we can work with. So that is called variable assignment. Okay. That's something you're going to be doing like day in and day out, anytime you're working in R. All right. So I want to now take a minute to talk about different data structures. Okay. So we've already talked about one data structure, which is a tibble or a data frame. What a data frame is, it's really not the most fundamental data structure in R. The most fundamental data structure is called a vector. All right. A tibble, it turns out, is a list. Fundamentally is basically a list of vectors. Okay. A vector is a collection of values. It can be one value. It can be thousands of values, anywhere in between. But the key thing here is that all the values have to be of the same type. All right, we've already talked about types. We've talked about characters and numeric types and factors. Whatever they are, they can be anything, but they all have to be the same. Okay. So let's show how these are made here. So, we can make a numeric vector. All right, and you know that these are number values because they are not living inside quotes. Okay. All right, so that's a numeric vector, pretty easy. And you can see down here, they show up without the quotes. We can make a character vector, also very easy. All right, now they're showing up with quotes. Let's say that I put in like A without quotes. It's not going to like that. It's going to treat that as an object. Okay, any sort of character value which is outside of quotes is going to be treated as a symbol or as an object. And if it hasn't been defined, it's going to give you an error. So error, object A is not found. All right, so we can't use that. Okay, so so that's easy. So we can also, as I said, one or any number can also be a character. So if you run that, you've now got one and it's treated as a character value here. Okay, you see it's living inside quotes. Now, I also told you that, vector has to be all the same type. So let's say we try to put, different types together, right? Well, that's not going to work. And actually allows us to do it, but it coerces this one to becoming a character. Okay, so you can see we tried to make it a number plus two characters, and it will coerce it for us. Okay, so those are vectors. All right, so very fundamental things you're going to be working with. So I mentioned to you that a data frame or a tibble is before I get there, another question. So what is the significance of the 1 in the front of each vector? Is this the vector's ID? So that's a great question. So Paulina is referring to this thing here. That actually just refers to the value. So that's like the first value is 1, and then the second value is B, and the third value is Charlie. All right, so I can, if I did this, so rep. All right, you'll see that it just recycles those values across the screen. Depending upon how wide the screen is, it will print out a certain number and then start over with the next one. So we're getting 9 values on each row, basically. Okay, so that's the 10th value, that's the 19th value. Okay, hopefully that makes sense. Good question. So, all right, so I mentioned that a data frame is a list or a sort of bunch of vectors stuck together. So let's say you wanted to extract one of those vectors. All right, well, I can do it like this. So I'm just going to work inside this one command here, the head command. So what you do is you say, all right, I want to take the second column out of demo data. Well, you use the 2 brackets, the 2 square brackets. That's the extract command. And there you go. So that's all of those values from the second column of demo data. Okay. Now we can just get the first few values by running this head command around there. So that gives us the first 5 values. That just keeps it a little bit shorter for us. All right, so we have some questions. So let's see here. The hands are raised. Sorry. Let me see here if I can get back to that. Let me. All right. Sorry, everyone. Figure out what's going on here. Stop the sharing for a second. And should we get some questions in here? Having some issues. Like something's